Hello, everyone. So we'll be starting the class shortly. I'll just mute myself for a few minutes until people can join in, and I'll connect my other device for Blackboard. So we'll start, and in today's class, there's like a lot of ground to cover. But just to recap, I think there was some glitch or something with uploading the files for week 2. I realized that they were not uploaded. I have just uploaded it again. I was checking something and I realized it wasn't uploaded. So apologies for that. I thought I have kind of uploaded it. Anyway, but there were some questions which I discussed last time, which were more on iterated elimination of dominated strategies, which as per your course structure actually you study only in this week. So even though I introduced the concept last time, I will go over it again today, and some of the questions, if you remember, had left it sort of partly solved. So we will solve it today. Okay, so let's get started. This is what we studied last time. We studied dominant strategies, Nash equilibrium, tragedy of commons, and mixed strategies. So there is a bit of a lag in the slide share, and this is, I don't know if it is because of the network or if it is just okay. I think it may be a network or a device issue. Anyhow, so just for the record, in case the internet breaks in between, like there is some issue with the internet in the middle of the class, please don't worry. It usually comes back on within a few minutes. So just join back again using the same link after 5-10 minutes, and we will resume the class. I'm just mentioning this in case that happens. Okay, so before we go to second prize sealed bid auction, I'll come to this. This is a very important topic and we will give it some due time today. But before that, I wanted to go over the example we took last time of tragedy of commons with n players, if you remember. Right? I had discussed the n player problem where there is a resource. You can normalize the quantity of the resource to 1, and there are negligible costs attached to extracting the resource. And the strategy of, say, player player I, you can say, is X, and we assume that all other players have strategy X1. So in that case, I had written this expression. I just wanted to clarify something here. So in this case, strategies are assumed to be same for all other players, but at the beginning stage, we cannot assume that my strategy as player I is going to be the same as the strategy of all other players, and that is the rationale I wanted to explain. So let me just rewrite. We wrote this last time. U of 1, player 1, in terms of X, or let's not use X1, let's use something else, X2, let's say. Okay, X and X2, or you can say X1 and X2. U1 is the payoff or utility of player 1 for his strategy X1 and strategy X2 of other players. Let's write this. X2 is other players. Okay. This we assume to be in proportion of my own strategy, so X1, and in proportion to the remaining resource. So that is 1 minus n minus 1 X2 minus X1, right? N minus 1 players have strategy X2, in which they're extracting the resource. That is n minus 1 X2 minus X1, which is what I am extracting. So if the total is 1, then remaining is 1 minus n minus 1 into X2 minus X1. This is my payoff. Now, the reason why at this stage we cannot equate X2 equal to X1 is because then it implies that I'm controlling not just my strategy, but I'm controlling all other strategies also. Because see, at this stage, what we're going to do is we're going to do del U1 by del X1. I'm maximizing U1 with respect to X1, which is my strategy, given X2. Here we are taking X2 as given, right? We are not assuming here that X2 is equal to X1, because assuming X2 equal to X1 here implies I'm controlling everyone's strategy, which is not the case, because this is a game. In a game, you can only control what you are doing. Even if other players are playing the same strategy as you, it is still not your strategy, right? It is not within your control. Which is why when we write this expression, we are going to write X1, X2 separately. And when we take the partial derivative, we take that also accordingly, right? So this comes out to be this equal to 0. And you can check the second order derivative. It is minus 2, which means this is the maximum. Okay, so then we write X1 in terms of X2, right? Yeah. In terms of X2, so far so good. This is pretty straightforward. Now that you have expressed, this is what, best response of 1 given x2 is this 1 minus n minus 1 x2. This is nothing but the best response of player 1 given strategy x2 of all other players, right? Now at this stage we can say that by symmetry, because since each player is going to do the same thing, does the same calculation, because we assume players to be identical in every aspect, right? We are not saying that some player will do something special, some player will do, no. You see, if there is no differentiation between players in the language of the problem, it means that they are identical, right? So that means that they are all going to do the same calculation, and therefore we can say, therefore we can take 1 equal to x2. Rational is important. So before I keep going forward, just want you to check if my sound is okay. You can just type in yes or no, because sometimes I realize after the video has been recorded that the sound was not coming out okay. If you can hear me properly, please just let me know. Or if you can't hear me, let me know that also. Sound is okay. All right, thank you. Just give me a moment. Okay, so at this stage now, if we take x1 equal to x2, the thing becomes a bit simpler, right? I mean, you will otherwise keep trying to solve a more complicated question without any need for it being complicated. So this becomes x1 equal to 1 minus n minus 1 x1 by 2. This is 2x1. Okay, let me just write it. 2x1, 1 minus n x1, x1. Right? Yeah. So x1, this is 1, this comes this side, n plus 1 is equal to 1. x1 comes out to be what? 1 upon n plus 1. This is x1. This is also x2. This is the strategy of all the players. Now, in this case, if you see what is the remaining resource, if you see the remaining resource is going to be what? 1 minus n times x1, because all n players are using this strategy now. We have assumed that at this stage. 1 minus n x1, which means what? 1 minus n by n plus 1. Now this is a very interesting result. Okay, let's say this is y, or let's say this is y1. Doesn't matter. You can use whatever notation you like. Now if you take limit of n tending to infinity for y1, if this is limit of n tending to infinity of n plus 1 upon n plus 1, isn't it? Or you can take 1 minus n by n plus 1. It's also the same thing. Let's leave it like this only. Easier to derive result like this. 1 is just 1. Now, if you divide the second term, you divide numerator and denominator by n. What do you get? 1 upon 1 plus 1 by n. N is infinity. 1 by n is 0. 1 by 1 is 1. So this is equal to 0. Which means that if there is a huge number of players all competing for utilizing that same natural resource, then in in a very short time, or you can say, like, we're not using time here, but in due course of time, the entire resource is going to get consumed and you will have nothing left, right? If the number of players is sufficiently large. So how large does that have to be? All that is a matter of discussion, but this is the general, the general outcome. And this part was sort of left out last time, and I don't think this was discussed in your lecture videos also. I don't think this is there in any of the books either. So I hope this is clear. And there is a similar question in the book by Prachi Datta, but I don't think he has discussed it like this. There's a slight difference in the framing of the problem. So that's why I wanted to clarify this. Okay, so if there are no doubts, I will go back to our second price sealed bid auction. Okay, so let's look at the second price sealed bid auction a little bit in a simpler setting first. Well, not that simple, but still, like, let's just say simpler setting. And what we do in second price sealed bid auction is, first of all, we define um, what are the strategies. Okay, so in this question, okay, the screen has not completed. I don't know why there is a lag. Yeah. Right. So in this case, there are two buyers. There are only two buyers, and they want to buy an antique piece of furniture. And it is known that it is a second price sealed bid auction. Now, their individual valuations are V1 is equal to 3 and V2 is equal to 2, where you can assume that these valuations are in thousands of dollars. And the strategies are bids VI, where I is 1 and 2. There are two players, V1 and V2. Both have the option of choosing a bid of 0, 1, 2, 3, or 4. Okay. Now, if they both bid the same amount, there is a tie, then we arbitrarily decide that P1 wins and he pays the bid amount. We have to find the Nash equilibrium or the Nash equilibria. So this is a slightly like cumbersome example, but I wanted to go over this because it helps you understand the reasoning behind the second price sealed bid auction. To directly go into that continuous valuation case, it sounds a bit confusing. It's a bit easier to develop the intuition if you go over it step by step. So I have, of course, made the payoff table, but I wanted to first go over how we make the payoff table. This is the payoff table, but let's draw this table. Okay, let's not look at the answer first. In price, yield, bid, auction. Okay, so let's make the table. It's going to be one slightly big table. Mm-hmm. Okay, now I'm sort of just drawing it up till because it kind of the valuations are such that beyond 4 making this table doesn't actually make any sense. But your question may have examples where they have the option of bidding higher than 4 also. But I'm just firstly it takes a lot of time to build this table like that, and secondly it doesn't make sense, and you'll see why. These are their valuations. It's important to remember. Now, first, let's write down what are their valuations going to be. Sorry, what are the utilities going to be? So, utility of player 1 when he's playing B1 and the other guy is playing B2 equal to, if B1 is greater than B2, then what is it going to be? If B1 is greater than B2, then it means that player 1 wins the bid. Right now he has to pay. Now how much amount is he going to pay? The amount he is going to pay is going to be B2 He will pay B2 because he has won the bid, but this is a second price field bid auction. So the amount he pays will be B2, the other guy's bid amount. And his net payoff is going to be what? His own valuation minus the amount he's paying. So his own valuation is what? V1. And the amount he's paying is B2. So V1 minus B2 if B1 is greater than B2. Okay. Let's move this little this side. This is okay. And if B1 is strictly less than B2, then who wins? B2, player 2 wins. What does player 1 get? Nothing. He gets 0. Now, in our example, if B1 is equal to B2, we are saying that player 1 is going to win, right? Because that is how the problem has been set up. So what happens is player 1 wins because they're both bidding, but whatever he has bid is equal to the other guy's bid. And now he has to pay that bid amount. So he's going to pay V1 minus V2. So instead of writing this second thing, we can actually just include it in the first case. So let me just rewrite this. V1 is greater than or equal to V2, we can write instead of just strictly greater than. Okay, so this is player 1's utility or payoff. Now let's talk about player 2. It's going to be very symmetrical, I mean very much similar. The method or the reasoning is the same. Here U2 for his bid B2 and the other guy's bid B1. If B1 is greater than or equal to B2, he gets what? He loses, right? If B1 is greater than B2, player 1 is going to win. Player 2 is going to lose. So he gets nothing. He gets 0. Now, if B1 is less than B2, then player 2 is going to win. If he wins, now he has to pay the other guy's bid amount. So he's going to pay B1 and his net utility is going to be his own valuation minus the amount he's paying, which is B1. So his valuation is V2 minus V1. That is his utility. So this reasoning, if you understand, all you have to do now is just to apply this reasoning in creating this. It becomes relatively simple. So let's just take a step back and think about what we have done so far. What we have done is we have identified who are the players. Players, we are given are players 1 and 2. There are only 2 players. What are the strategies? We've identified the strategies of the 2 players, which is their bids. They are bidding. Third thing which characterizes every game is their payoffs. Payoffs are very important. And what are the payoffs in this game? So in this game, of course, we will make the game table, but we have to write down how we are calculating the payoff in different scenarios first, because the payoff is not given to you directly. You have to calculate it, right? So whenever you have to calculate the payoff, you need to first be clear about how the payoff is going to be calculated. And in a second price field bid auction, you know the rules of not the rules of the auction. When they tell you second price field bid auction, it's just by using that expression, they're telling you the rules of the game and hence how the payoff is going to be calculated. So this is how you calculate the payoff. Now, you know the players, you know their strategies, you know their method to calculate payoff. Now you can fill the table. Once you fill the table, I will come to what the table is going to be. But once you fill the table, then what will we do? We can, if we want, we can check for dominant strategies, or we can just use the plain old simple best response analysis. And in this particular case, actually, best response analysis is slightly more easy option, because you may sometimes end up eliminating strategies which don't have to be eliminated. So, elimination of iterated elimination of dominated strategies is very good method when you are quite clear about strict dominance. If it is a strict dominance, it is a pretty simple, straightforward thing. And if you're sure it's a mixed strategy game, then also you can do it. But in a game like this, it's a little bit risky to use iterated elimination of dominated strategies. At least that's my approach. So we'll do the best response analysis, and then we'll just see what are the intersections of the best responses. Okay, so if they both bid 0, nobody wins, so they get 0 and 0. Okay. Now if P2 is bidding 0, right, and P1 is bidding something else, what is going to happen? P1 is going to win, and P2 is anyways going to lose. He's bid 0. So P1 is going to win, and if he is bidding 1, he wins, and his valuation is what, 3. But what is he going to pay? He's going to pay 0 because the other guy has bid 0. So he is going to win, and he gets 3. If you see, in all of these cases, the payoffs are going to be 3, 0. You get it? Irrespective of whether he bids 1 or 2 or 3 or 4, the other guy is still bidding 0 and he is still winning. So whatever he bids, in the end, he is going to pay 0 only. So his payoff is 3. Similar logic, if you see the first row, if P1 is bidding 0 and P2 is now bidding something else other than 0, then if he bids 1, he wins the game, right? And P1 is bidding 0, so now he pays 0 because the other guy is bid 0. And his valuation is what? 2. So he is going to get 2. And similarly, in all of these cases, he's going to get a payoff of 2. Okay. 1 and 1, again, there is a tie. So in the situation where there is a tie, these dotted boxes are the situations where there is a tie, where they both bid the same amount. And when we have, as per the rules of the game, if they both bid the same amount, P1 is going to win, right? And if P1 wins, he's going to pay the bid amount. So if 1 is the bid amount, then P1 is winning. His payoff is 2. This is 2, 0. If the bid amount is 2, his payoff is 1. This is 1, 0. And if payoff, even if he's bidding 3, payoff is 3 minus 3 equal to 0. And the other guy is anyways not winning. So his payoff is 0. He bids 4. Okay. And they both bid 4. And his valuation is only 3. So now what happens? He has to pay 3 because he has to pay 4 because the other guy has also bid 4. Now his payoff is actually negative. And the other guy doesn't win or lose. He just gets a 0. These boxes are pretty straightforward. The rest of the boxes, again, you will fill using the similar logic. P1 is bidding 2 and P2 is winning 1. See, all these boxes under this, you can say, how do I draw this? Let me use a highlight. Okay, so these are the boxes in which the result is tied, right? Now, all the boxes under this, what is happening? P1 is winning because P1 is bidding higher, right? So 1 is bidding 2, 2 is bidding 1. The valuation is what? 3 minus 1, 2, 0. 1 is bidding 3, the other is still bidding 1, 2, 0, 2, 0. Okay. The other guy is bidding 2, he is bidding 3, he wins. It is 3 minus 2, 1, 0, 1, 0. And if he is bidding 4, the other guy is bidding 3, he wins, but he pays 3 this time. Okay. So it is 0, 0. Similarly, you can calculate the rest of it. So if P2 is bidding 2, 1 is bidding 1, P2 wins, he gets what? 2 minus 1 equal to 1. This guy gets 0, 2, 0, 1, 0, 1. And if P1 is bidding 2, he is bidding 3, he wins, but now he has to pay 2. 2 minus 2 is 0. 0. This is also 0. And if he is bidding 4 and the other guy is bidding 3, he wins, but now he has to pay 3 and his own valuation is only 2. So he is going to pay extra. He's going to get a valuation of minus 1. So see, this is not very difficult. Once you understand the rules of the game and the rules of the game are like clear in your head, the payoff table does not take a lot of time to build. So even if you have like, oh sorry, something. Just give me a moment. It's not supposed to be, yeah. The I'm trying to make sure there is no echo. Yeah. So now coming back to where we were, like I was saying, if how you build this table is clear to you, you will not be confused. So if you are given a second price seal bid auction and the bidding strategies are discrete amounts like 0, 1, 2, 3, 4, whatever, then you will use this methodology and you will build this table and then you will do the best response analysis. So now let's go to this table. So this, let's see if this is the same table. It's the same table, right? What I just wrote down. The lab. Why the screen is not updating. Okay, so this is the table, and as I was saying, I have left the white boxes as is. These are the boxes where they are tied. You will follow the rules given in the question for these tie situations. In our example, it's given then what that one wins, so we have calculated payoffs based on that. The green boxes are all the boxes where player one is winning, and the pink boxes are the ones where player two is winning. So far, so good, right? Now we will calculate the best responses. Okay, so if player two is playing 0, then what is the best response here? All these responses, because they're all giving the same payoff, right? Anything more than 0 is good. Player 2 is playing 1, then all these are best responses. Player 2 is playing 2, and for player 1, all these are best responses. Player 3 is playing, player 2 is playing 3. Then it doesn't matter what he plays, because no matter whatever he plays, he gets only and only 0. So all are best responses. Player 2 plays 4. Again, other than this -1 payoff, which is 4, all others are giving 0. So all are best responses for player 1. Now let's go to some other players. Let's look at player 2's best responses. If player 1 is playing 0, similar logic, he's going to any strategy other than 0 because they all give a payoff of 2, which is higher than 0. Player 1 is playing 1, then 3, 4 are giving him a higher payoff. These are the best responses. Player 1 is playing 2, then everything gives a 0. Right? All of these are best responses. So I would really strongly suggest that whenever you're doing best response analysis, please circle the best responses with a pencil or some colored pen or something, because don't try to do it all in your head. It doesn't work. I mean, even if you're extremely clever, it is still possible to make a mistake if you're just trying to mentally calculate it. Don't do it mentally. Either you can underline them or circle them or whatever, but do it on a paper or your tab or whatever. Don't do it mentally. Now, if player 1 is playing 3, then player 2 is going to play anything other than strategy 4 because that gives him a -1 payoff. And if player 1 is playing 4, then player 2 doesn't care what he is because everything gives him a 0 payoff, right? These are all your best responses. Now, all the boxes in which both the players are playing their respective best response, they're all Nash equilibrium. So I have just represented it in a little neater way in the next slide, like this. So you can see all the numbers are colored, whatever are the best responses. And all of these are Nash equilibrium. Now let's try to represent this on a diagram. Okay, this diagram is a little bit tricky. Okay, so try to understand what we mean by a best response. What we are plotting are best responses. Okay, on the x-axis you have bidding strategy B1 of player 1. Y-axis you have bidding strategy B2 of player 2. And what we are plotting are best responses. So the green lines are the best responses of player 1, and the red lines are the best responses of player 2. Okay. Now, if you see, I have marked V2 and V1 here. You can check. This is 2, this is 3. I actually put this on a grid, but the grid is not, it's not visible slideshow. So I mean, if you want, I can go over this, but if you plot just these values, that's all. For P2 equal to 0, what is P1's best response? You plot that. Then for P1 equal to P2 equal to 1, what is P1's best responses? You plot that. Just do that, and you will get a diagram like this. And I mean, in this question, maybe in your MCQs, maybe you don't need this diagram, but drawing this diagram, that exercise, a mental exercise of plotting this diagram, kind of clears a whole lot of cobwebs. You will understand. Now see, in this diagram, you can see visually all these nodes where all these red and green lines are intersecting. Okay? All these intersections, not the ones where there is just freestanding, but ones where they're actually intersecting. These are Nash equilibria, right? So making a diagram kind of gives you a sense of what we are really doing here. Otherwise, it just looks like just numbers. You're just adding and subtracting numbers. When you look at this, it makes sense, right? So I will make another similar diagram like this, and I'll spend a little more time on that in the continuous time case. But this is the diagram for the discrete time problem. I've already made it. It's already there in the slides, and you will get this right after the class. But I would encourage that you check this diagram. You try drawing it yourself and see if you're getting the same diagram. Don't look at the diagram. First, just try to plot this payoff table yourself on this kind of an axis. Even if you get stuck, you can of course ask me in the next class. But you can draw it yourself and check if you're getting the same diagram. Now we come to the seal price, second price sealed bid auction in continuous time, where we have the same two buyers and they have this valuations V1 and V2, and this time we don't know V1, V2. We just know that V1 is greater than V2. Okay, and their strategies are BI, which belong to 0 and infinity, meaning they can bid anything from 0 to infinity, any positive number. And if they both bid the same amount, then P1 wins and pays the bid amount. Just exactly the same rules as we had before, except that V1 and V2 are unknown, and the bidding strategies can be any positive number. They belong to, you can also write it like this, BI belong to set of positive real numbers. Okay, so I'll come to this. First, let me write down the continuous time case. Okay, so now in continuous time case, actually whatever we did so far, this part which we wrote here, this part which we wrote here, payoffs, the calculation is the same, right? Only V1 and V2 values are unknown. The calculation for payoffs is actually the same. If you see, this payoff calculation, you don't need to redo actually. That's why I went over it in the first part itself, that if you understand it in the first part and you kind of absorb how it is being applied in the game table, then the first part, calculating the payoff part, is already written out for you. Now let's do the rest of it. Let's talk about the best responses. So let's write down the best responses of one given V2. Okay, so we have already written down payoff. So based on the payoffs, we are going to write down the best responses. So now let's see the best response of one in, in the case where we will of course consider whether V1 is greater than V2 and all that, but also see what is happening here. Let's pay a little bit of attention. Let me highlight this and this. So in this case, the payoff is V1 minus V2 for clear one. We're talking about U1 here. The payoff is V1 minus V2. So we will need to consider the case when V1 is greater than or lesser than V2, because we don't know V1, right? We don't know V1 and we don't know V2, and we don't know V2 and V1 either. We don't know the valuation and bits. Even though we know that the payoff is V1 minus V2, now in this case, in the continuous time case, there is another, you can say another problem or another consideration we need to take, which is the case in which V1, my valuation, less than the bid made by the other guy. Then what is going to happen? My valuation is less than the bid of the other guy. Then if I end up winning the bid and if I end up paying the bid amount of the other guy, I'm actually on the losing side, right? Which is what was happening here. When I made a bid of 4, I'm P1, I made a bid of 4, and the other guy also made a bid of 4, and I had to actually pay 4, which was the bid of the other guy, and it was greater than my valuation, which is 3. So if I make a bidding, let me highlight this. So if I bid this amount 4, and in this case, I mean, it's not about whether I bid it or not. It's also the fact that I won. So even if I bid 5, for example, just hypothetically speaking, I'm still going to get minus 1, 0, because if I bid 5, I win the lot. I mean, I win the auction. But now the other guy has bid 4, which is more than my valuation V1. So I'm going to go into negative payoff, which is minus 1, 0. So this game table was only till 4 to characterize the game properly, but now in this continuous time game, you can bid anything, right? So now 5 is also a possible strategy, 6 is also a possible strategy, anything is a possible strategy. So here, now when we're writing the best responses, we are going to pay attention to this aspect of the game, which is when is his payoff positive, when is his payoff 0, when is his payoff negative, right? So, okay, 1 minute. Assuming my valuation is V1, I would never bid V1 much greater than V1, since I may have negative payoff. So the case V2, no, that is not true. We are not considering that. We have, when you're writing the game, see, in the end, whether you will bid it or not is a different matter. Okay, these are two different things in game theory, and it's important. It's good you ask this question, because there are two different aspects. See, in a game theory, first, when you're characterizing the game and you're writing payoffs, you cannot assume that I'm never going to bid higher than my valuation. Why? Though, haven't you seen so many movies in which people go and bid amounts which are much higher than their valuation? Firstly, it is not true that you will not bid higher than your valuation, because you're not paying your valuation, you're not paying your bid, you're paying what the other guy is going to bid. You have to remember that. And you don't know what the other guy is bidding. It's a sealed bid auction, right? You don't know what the other guy is bidding. So if you are bidding a higher amount, I'm bidding 6, okay? The other guy is bidding 3, okay? I win, but I'm paying only 3, right? If my valuation is 5, and I'm bidding 6, I'm bidding higher than my amount, my valuation, but I'm paying only 3. So yes, of course, I will bid higher than my valuation. You're getting me? So firstly, even if this were not the case, you will always consider the possibility and then eliminate it if the payoff is negative. But at this point, when we are characterizing the best response analysis, you cannot eliminate it outright like that. You have to write that case. You have to create all those separate cases in which the best response which is what we are going to do. So this is why I'm bringing up this discussion, that when you're writing the best response analysis, you have to consider every possibility. And this is only a second prize sealed bid auction. When you go into extensive forms games, this logic becomes even more important, as you will see in the next few weeks when you're talking about some games, subgame perfect equilibria and all that, and multiple branches of game in a game 3. You will be considering imaginary strategies which don't actually exist, because you have to consider all possible strategies and all possible outcomes. Even if you're talking about, even if you think some strategy is dominated, you will still consider that case. This is not a guessing game. Game theory is not a guessing game and it is not a game ki main kyun bid karunga. No, it is not like that. This is beyond your everyday logic. Okay, there are some things which are everyday logic, but some things in game theory are very counterintuitive. They're not your everyday logic at all. You're talking about bidding higher than your valuation. What about people who continuously use credit cards and they don't have the money to pay the credit card bill? People do that, right? And logic is only to maximize your payoff. So if in some world, if in some if in some context that is maximizing your payoff, you will do that. Okay. So I hope I have addressed that doubt. My only thing is that you need to consider all the cases. After you have considered all the cases, then you will delete strategies which are implausible. Out at the outset, you cannot eliminate it. I haven't even written the best responses yet. Without writing the best response analysis, I cannot eliminate any strategy. That is all I'm saying. What somebody plays is based not just on what they play, but on what the other guy is going to play. That is why it's game theory. So I think I have explained this. So if V2 is greater than V1, that is exactly what we're trying to characterize over here. Then V1 will bid less than V2 because he doesn't want to pay negative. But you cannot eliminate that case, is all I'm saying. His best response is not going to be that in this particular case. But like I'm saying, you cannot have a mental block about it. That doesn't work, because sometimes in this example, your intuition may be right, but in some other example, your intuition may be completely wrong. So you always have to consider then the case, then you see what the payoff is, and then you write down what the best response should be. So if you have something like should be V1, I think. So here, because you see, if B1 is greater than B2, then you have B1 minus B2 as a payoff. And if B2 is greater than B1, then you are going to want to actually bid B1 less than B2. Okay. Then if B2 is equal to V1, whatever he bids, it doesn't matter, because he's, if as long as he's bidding, and as long as he's winning the game, he is going to actually, this is actually equal, right? B2 is equal to V1. Now you have V1 minus B2 as the payoff. His payoff is 0. So he's going to have this response. He can play any strategy. Okay. What was I writing? Yeah. So if B2 is less than V1, then he will play B1 greater than B2. So this is how the game actually works. Because you see, even if B1 and B2 bid the same amount, one is actually winning, right? So this is how your best response comes out to be. And similarly, if you want, you can write down the best response of the other person also. Okay, now 2, payoff of 2 is what? If B1 is less than B2, his payoff is B2 minus B1. Otherwise, it is 0. So what we are going to write is we are going to write it in terms of V1 and V2. V2 is his value, A shift. So if you have V1 is greater than V2, then his strategies are going to be to bid less than, let's not put equal right now, to bid less than V1. You can put equal also because, as we said earlier, P1 wins the game if they are equal. Now, if B1 is equal to V2, then what happens? Then again, he's indifferent. So let's say 0, infinity. And if B1 is less than B2, then of course he wants to win the bid. So he is going to bid some amount greater than B1. So this is our best response analysis. And shrink this. So if you see this analysis, if you take some time on your own and you compare, it is going to match what we did in this game table here. What we've done in the game table is very much in sync with or in line with this kind of analysis. Okay. Now, what we'll do is, now this time I will try to plot it. So although I have actually already plotted it, but let me try to plot here also. V1 this is V2. So what I'm plotting here is going to be a bit rough because it's not so easy to get this perfectly in a manually drawn diagram. Just for explanation purpose, the proper diagram is there in the slides. Okay. This is your 45-degree line. So it's not some important line, it's just a 45-degree line. No, we plotted the best responses earlier also. The diagram I had in the slides, that's what you're referring to, right? We did not plot the payoffs. We plotted the best responses, function of the strategies. They're two very different diagrams. If you sit down and draw the payoffs, you will see that the diagrams are very different. Best responses is, what is my strategy given the other guy's strategy. Okay, so now I'm going to just shade it because otherwise the whole diagram gets a bit. Okay, so now let's see. Now this is kind of like straightforward from here. Best response of 1. 1 means the first guy as a function of 2. So what he is going to do will be decided based on the value of 2. If B2 is greater than V1, so B2 is greater than V1 in which region? This region B2 is greater than V1. Right? If B2 is greater than V1, then V1 decides to play less than B2. Okay? See, if B2, I'm talking about this first part here. If B2 is greater than V1, I've made this green highlight in that whole region. This whole part is B2 is greater than V1, right? This is the V1 line. I will erase these later on, but just for now, I'm explaining this. In this whole part, what this guy wants to do, V1 wants to play a strategy of B1 less than B2. So what 1 is going to do, let's use some other, let's use this color. So he's going to do this. The whole region is under that in this whole region, B2 is more than B1, right? And even here, region, B2 is more than B1, right? Okay, this is the line. We'll come back to this line later. We can perhaps delete this part. Deleting part you can do, even if you don't do in the eventual answer, it won't matter in this particular case at least. Now in the remaining part, you can see the rest of it. If B2 is less than B1, which means this side of the curve now, what one wants to do, B1 is greater than B2. So, in this part, one is greater than B2. That is a strategy he or she will want to play with. This should be in the same color ID. So I drew it properly in the the slides because this gets very, very messy. So let me go to the slides because this diagram is already looking very messy. So this is your basic framework. This is your diagram. Okay, let me explain it here itself. So this is your framework. The green regions are the best response of 1, and the pink regions are the best response of 2. So it's what I just shaded. You can see this green region, this lower part is what I just shaded, and the upper part is what I was still shading while we were talking. And the next part, you can see the same, you use the same rationale which we used if you read this part. So if you read this part, the best response of 2, you can use this reasoning. If you use this reasoning, you will get this shading pink region. Okay, it's not very difficult, but just spend some time thinking over it. Just like how we did the green region, similarly, you can do the pink region. Again, slide is not updated. Glad. Yeah. So this part, all this region where pink and green are overlapping, this part, all of these are your Nash equilibria. So all the points in this region are in Nash equilibria. Why is that? Nash equilibria is when both the players are playing their respective best response. Okay, so I hope this is clear. I've taken the example of the second price yield bid auction because it's a little more confusing and it's a little tricky. If you want, you can do a similar analysis for the first price yield bid auction also. In that, it is relatively much simpler because the amount you pay is not it is not the other guy's bid, but it is your own bid. So everything becomes much simpler. You will bid right up to your valuation and not more than your valuation, because of course you're paying what you're bidding. If you're paying what you're bidding, it is pretty straightforward. You know what's your limit, so to say, right? It becomes complex. It becomes more interesting when you are paying what the other guy is bidding, and at the same time you may or may not win even after bidding higher than your own valuation. So that's why I took the more complex case. The simpler case, I think, should be much more easy to solve now. Okay, so I think we have been going on for almost an hour. If you have any questions, please tell me now from whatever we've discussed so far. After this, I will go on to, if you want, I will discuss this two firms problem. And then we'll talk about the Braess paradox and something else. I don't remember what else was there. Yeah, the hoteling problem, the median votive theorem. Okay, so I will do one thing. I will come to the Braess paradox and median votive theorem first, because I think that is the newer thing in this week. If time permits, I will solve the two forms that iterated elimination of dominated strategies also. If not, then I will just post the solution. I just wanted to check. I kept it in the slides in case we get the time. I wasn't sure how much time it was going to take. Okay, so I will just mute myself for 5-10 minutes. Please stay tuned. I will be back and then I will discuss the two things we discussed. Okay, so we'll continue. We are going to now look at a problem which is an example of the Braess paradox. Not exactly a paradox, but sort of like a counterintuitive social outcome. So what happens in the Braess paradox is that, say suppose there are two routes. There is a route ACB and another route ADB between 2 points A and B. Now these are both roads. You can assume they're both roads. Both the roads have certain patches which are, say, under construction. Okay, or we can say that these are two bridges which have some um, traffic jam kind of a thing or something like that. Okay, so there are these two patches. I've marked it with these sort of barricade kind of thing on the diagram. They are in the locations shown on the diagram, and the traffic is slower in these patches. So the travel time from C to B and A to D is 15 minutes. So the parts of the road which are kind of clear, which don't have any problem, travel time across those parts is 15 minutes. The time to cross parts of roads under construction, that is A to C and D to B, is X by 100 minutes. X is the flow of traffic per hour. What we want to know is what is the travel time from A to B. Okay, and the next part is, if you build an expressway like so as shown in the figure, where traffic can only move from C to D via E, it cannot move from D to C. It can move only in one direction, C to D via E. Then what is the new travel time? We'll come to the second part, but for the first part, so think of this as, if you want to sort of understand the logic or the intuition behind this particular game, is that suppose you're in a traffic jam and there is a multi-lane road. There are like 3 lanes, 4 lanes, something, and there is there's some roadblock or something much ahead in the road. You'll see that the cars will keep readjusting between the different lanes. If one lane moves even a little bit, number of cars will go and join that lane until all the 4 lanes are again back to the same speed. Similarly, if some other lane on this side starts moving faster, some cars from this side will immediately turn around and go and join that lane until all the 4 lanes are again back to status quo. They're again back to the same speed. And this is something you can see in traffic all the time. This is also I think in some places it's called a traffic jam problem also. So this is like a very natural, naturally observed situation everywhere. So maybe not in countries which have very strict traffic rules and you can't jump lanes or something like that. But even in those countries, I think in a traffic jam, people do the same thing. So this is that sort of a logic here, which means that, if A to B were faster, ACB were faster than ADB, what happens? Cars, some of the cars from ADB will jump to ACB instead, from A. Eventually, the travel time across both the routes will be the same. As long as there is some difference in travel time between the two, cars will keep readjusting, redistributing, so to say, between the two routes until the travel time between the two routes is again the same. So we will solve this by using that kind of logic here, or that intuition here. So this is the Braess paradox, named after the guy Dietrich Braess. Dietrich or Dietrich, I don't know. I think it's Dietrich for German. I'll just roughly draw the diagram again. And this is the part of the road which is logged. We'll make a highway E here, but let's not go there. The speed here is X by 100. Here it is 15. Similarly, here it is 15 and here it is x by 100. Okay, let me just check if I've got that right. Okay. Cars, flow of cars is 1000. Cars, let's just write 1000 for now. We're doing everything per hours only. So let's assume that, X cars are going in route C. 1000 minus X cars go via ADB. Now we know that the traffic or travel time is the same. So what you will do is X by 100 is what? X, we've taken it as X only, so it's X by 100 plus 15 is equal to 1000 minus X by 100 plus 15. Now if you can see, there's a timings across these patches, X by 115 is symmetrical, a very symmetrical problem. So eventually what you get is X is equal to 1000 minus X implies X is equal to 2 means 500. So you know the number of cars on each route, which is 500, means the equal number of cars are going via both the routes. Now the travel time is what? Therefore, travel time by either route is equal to 500 by 100 plus 15, which is 20 minutes. So we know that the travel time is 20 minutes right now. Okay, so now what happens is that this new expressway is built, and since cars can move only from C to D, we know that the route they will take is this and this, and then okay, it's not so visible here, but you will see in the notes I will upload, this will become kind of visible. I just prefer the dark background, that's why I don't like it like that. It also gives a little more of a blackboard feel, I think. Anyway, I prefer a dark background. It's less taxing for the eyes. So anyway, so now we know that there are cars going through this route. We have this option of taking this route, and we know that the travel time via this route, this expressway, is 2. Take 2 minutes to cross CED, right? So now this problem, you actually, if you try to solve it mathematically, you won't really end up anywhere. This problem is sort of not that straightforward to be solved mathematically. So what we need to understand here is that in this, in this problem, the rationale is that this is an expressway, right? The travel time through the expressway is reduced to 2 minutes. So when people enter at A and they know that they have this option of taking this expressway and going via E in 2 minutes, they think this is a better option, right? And assume that they are right. Okay, this is a better option. So they will enter at A, they will go to C, D, and then E. So what it looks like a tempting option, so they take that option. Now let us see whether this can be an attainable equilibrium. If they take the route C DB, travel time, presuming now that all cars are going via this route because the other routes don't look that viable to them, looks more, right? Like I said, 2 minutes across the expressway. So everybody goes there, and travel time is X by 100 2 x by 100. Now the cars here is 1000. So this is 10 plus 2 plus 10. The time is now increased actually to 22 minutes. You might think that, then why will they go this way? Why won't they go that way? Now the problem here is that the other options in this new scenario, that expressway, is also not viable. Why is that? Now say suppose this guy who he's wondering if he should take the other option. Everybody is going through the expressway, and he's wondering if he should take the other route, ACB. Let's say one guy wants to calculate travel time via ACB in new scenario. What is going to happen? This actually works both ways. ADB have the same calculation, so it comes out to be the same. Now what happens here? The travel time from A to C is x by 100. Now the cars here is 1000, right? 1000 by 100. The travel time from C to B, which is 15. This comes out to be 10 plus 15, which is now 25. He has no reason to deviate, right? If he wants to deviate to route ACB or ADB, now his travel time has increased on both these routes. Earlier it was 20 minutes, now it is 25 minutes. So what is happening? We see is that now the only desirable outcome, the only equilibrium outcome possible is ACEDB. Because on any other route, because the number of cars has also increased on these patches, right? A to C and D to B, the number of cars is all the cars, is 1000. Even if on the stretch C to B and A to D, there is only one car, travel time is still 15 minutes. On the other two stretches, the number of cars is now 1000, double. So the travel time has increased from 20 to 25 minutes for this particular guy. So he has no incentive to deviate. His only three options are ACEDB or ACB or ADB. Now between all the three options, ACB, ADB are giving 25 minutes time and ACEDB is giving 22 minutes time. Of course, he's going to take ACEDB, and that is the logic which all the motorists are going to use, right? Not motorists per se, but all the people commuting are going to use the same logic, and hence new travel time is going to be 22 minutes. And this is called a paradox not because it's actually there's some opposite of opposite or something, but because this is not the expected outcome. You think that you're building an expressway, the travel time will be reduced, but it's not reduced. Now, of course, there's a solution to this. Instead of this direction of traveling, if people could do A, D, C, B, even then actually the travel time is still going to be very high, but still. You see, if you take A, D, somebody had posted this in a comment somewhere. Take the route A, D, C, B, then your travel time is anyways fixed. It is what? 15 plus 15, 30 plus 2, 32 minutes. It's even more. So even if you allow cars to go backward like that, the time is still very high. So in this problem, cars can move in only one direction. But even if you do allow cars to move in the opposite direction, travel time is still much higher than the other options. So we know that only Nash equilibrium possible is ACEDB. But of course, this problem can be redesigned in real life. It can be redesigned in such a way that you don't get this kind of a socially non-viable outcome. That is why we study game theory, so that we don't get into these kind of scenarios where you're getting the opposite of what you wanted to achieve. Okay, next I will go to the median voter theorem. And I'm not taking the continuous time case because it's a bit difficult to intuit the continuous time case. It takes a little bit of imagination, you can say, to intuit the continuous time case. But once you understand the discrete time case, I think the continuous time case is very similar. So it won't be very difficult to understand. Even this is not exactly discrete time, but I mean, it's still not as complex. Okay, so this is very similar to the ice cream cart example in the lectures, but it is a classic theorem on its own. It is not exactly the same as the ice cream cart problem, but it is, the rationale is very similar. Okay, because in that ice cream cart problem also, the ice cream sellers are trying to maximize the market share, or the number of users who buy ice creams from them. And in this median voter theorem also, you have two political candidates, and they're also trying to maximize the voter share, number of people who vote for them. So in the ice cream cart question, the two players are selecting a physical position between two locations, A and B. Whereas in the median voter theorem, they are selecting their policy positions, not physical locations, but policy positions. But mathematically, they come out to be very similar. Okay, so now I've taken this as an imaginary problem because I mean it's not like it's actually imaginary, but so that there is no conjecture about policy positions and things like that. There's, if you, I don't know if you watch Star Wars, there is a planet called Jakku in Star Wars. So I've just set this problem in that planet. This is not a question from any book, just so you know. So on this particular planet, Jakku, there are two political candidates, P1 and P2, and they have a choice of policy positions like what's given. So Pi belongs to, you can say 0, quarter, half, 3/4, and 1. Where you can say 0 is the extreme left of Jakku and 1 is the extreme right of Jakku. Okay, whatever their left and right policies are on that particular planet, these are the distributions. That's what we are concerned about. Okay, and voters are uniformly distributed between these policy spectrum, policy positions. And I don't know if it's clear from the language of the problem, but what we're trying to say is these are the only policy positions. All policy positions on that particular planet can be characterized between this particular spectrum we have laid down as 0 to 1. These are the brackets. So, you can think of it as the extreme left is say 0 and extreme right you can take as 100%, and you can do it that way also. It comes out to be the same. It's mathematically easier this way. We are assuming that, so there are 5 policy positions, right? 0, quarter, half, 3/4, and 1. And we are assuming that all the voters on Jakku are, divided up into these 5 positions. So there's 1/5 of voters at each position. So you can assume that each of these positions has 1/5 voters. Now, the rules of the game are what is interesting in this problem. So the voters here are pretty committed to their ideologies. Okay, they will only vote for one candidate first of all, or they also have the option of voting for neither. And when do they do that? We'll just see that. So the voters will vote only for the candidate who is closest to their ideological position, as long as the candidate does not differ more than 0.5 from their ideological position. If there are voters at say a quarter, they will not vote for anybody beyond 3/4 position. So if there's a candidate at 1, people at located at a quarter are not going to vote for that candidate located at 1, even if that candidate happens to be the closest candidate. Okay, I'm just explaining what that clause means. If both the candidates are equally close, if both the candidates are say at the exact same position, there are only 5 now. If out of those 5 both end up at the same position anywhere across the spectrum, then the voters divide their votes between the two of them. They're equally divided. And the candidate with the highest vote wins. So we know what they want to do. Now we want to find the Nash equilibrium strategy of the two candidates. Okay, so let's characterize this. Okay, so let me draw this line. So we'll be drawing a lot of diagrams because I want to show all the different cases that can kind of arise. But let me just draw the first diagram to explain the setup. This is policy position 0, 1. Center you have half. This is quarter. 3/4. And let me write down the populations in a different color. So you have 1 by you have 1 by 5 here, 1 by 5 here, 1 by 5 here. Total comes out to be 1. Okay. So these are all the policy positions. I'm drawing this just to sort of show the vote share. Okay. Now there are two candidates, say P1 and these are the colors I'm using for these candidates when I'm showing their votes. So when I show the votes for the candidates, I'm going to use these respective colors. Okay. Now let's see what are the options for these guys. What they want is to maximize the vote share. Each candidate wants to have as many votes as possible. So in the scenario, let's start with the scenario where they are both at the extreme ends. Okay. So say suppose P is here and P1 is here, then what is going to happen? So what about the candidate? The candidates are at P1, are at 0 and 1. Now, first let's be clear about what is the structure of this game. So who are the players? Players are P1 and P2. This is important to remember. Believe it or not, many times people get confused between who are the actual players in a voting game. Sometimes the players in the voting game are actually the voters. Depends on the question. In this particular problem, the players are the candidates, not the voters. Okay, it's an important point. Candidates are the players. The policy positions are their strategies. Okay, we need to clearly identify what their strategies are in a game. Payoffs are number of votes, and it's not exactly you can see number of votes. The payoff is the objective is to maximize the number of votes. So the maximum, so the number of votes is the payoff, you can say. We are trying to maximize that. So this is the setup of the game. Now let's see what happens if P1 is at 0 and P2 is at 1. All the voters are at 0. The closest candidate is who? P1, right? So all voters 0 are going to vote for P1. I am marking this full line to indicate that all the voters, all 1 by 5 voters at 0 are voting for P1. 1 by 4, again for people at 1 by 4 here, closest candidate P1, and P1 is within 0.5 of their policy position, right? So all the people at 1 by 4 will also vote for P1, isn't it? Let's move to half. Now people at this position half, for them P1 and P2 both are equally close, right? Both are equally close and they're both within 0.5 of the policy position. Is that so? So half of these people will vote for P1 and the other half will vote for P2. The other half are voting for P2. So this is how I have shown it, that the people, the population at policy position half of them are voting for P1 and the other half is voting for P2. Now let's look at the population of 3 by 4. For them, P2 is the closest candidate now, right? So they're all going to vote for P2. People at policy 1, of course, P2 is the closest candidate, so they're all going to vote for 1, for P2, sorry. This is the distribution, you can say. Now you can show it on a graph in whichever way you like, but because I've set up this problem in discrete time, I've just shown it in, in a discrete format. Let's see what happens if P1 decides to move. Okay, so now if P1 decides to move, let me just redraw this. We can compare it. This is what we're going to do in this median voltage theorem and similar kind of problems. We sort of first characterize and lay down all the policy for all the possible strategy positions. And then we see what the payoffs are at those positions for all the players. And then we see if they have any incentive to deviate. Because the Nash equilibrium is when there is no incentive to deviate. Okay, so let's say P1 moves to this point now. Now P1 is standing here and P2 is still in the same place. Okay. You can see P1 has moved to this position 1 by 4. Okay, P1 wants to see what happens if he moves from extremes left from 0 to 1 by 4. He wants to see what happens to his vote share. Let's see what's going to happen. For people at policy position 0, who is the closest candidate? It's still P1, right? They're all going to vote for P1. Still, people at 1 by 4, P1 is, of course, the closest candidate. All going to vote for P1. People at half, now see, for people at half now, P1 is the closest candidate. P2 is no longer the closest candidate, right? P1 has moved closer to them. They're all going to vote for P1, right? Now, people at 3 by 4, now people at 3 by 4, for them, P2 is definitely the closest candidate. P1 is now, even though P1 is within half of their policy position, but still they will vote for the candidate closest to them, which is P2. So now people at 3 by 4 will still vote for P2, and people at 1, definitely they're going to vote for P2 because he is the closest candidate. So now what happened? The vote share of P2 is 2 by 3, whereas, sorry, 2 by 5. As vote share of 1 is now 3 by 5. He has increased his vote share, isn't it? In the previous problem, you can say this was half and this was half. They were both getting half. Now he's getting more. So by a similar logic, if you think T2 will also use the same rationale, he will also want to move to 3 by 4. Right? So now if you want, we can again look at what happens if they both move to quarter and 3. If P2 also moves to 3 by 4, let's redraw this. See, this is how we are going to proceed. It's not rocket science, but you do have to do it systematically, step by step. Can't assume that this is going to be the outcome. And also remember that people have the option of not voting for anybody. I've not seen that sort of in the problem so far, but it can figure, right? Let me write this above. So P1 is now at 1 by 4. P2 has moved and is now at 3 by 4. Okay, so now this time P2 has moved. P1 is in the same place. So now 0, people at 0, they're going to vote for P1. Pretty straightforward. People at 1 by 4, they're going to vote for P1. He's the closest guy. People at half. Now see, again, they're in a quandary. P1 and P2 both are equally close to half, and they're both within half of their policy position. So again, the people at half are going to, half of them are going to vote for P1 and the other half are going to vote for P2, right? People at 3 by 4, they are going to vote for P2 because he's the closest guy, and for 1, people at 1, they are again going to vote for P2 because he's the closest guy. Now what happens? Again, the votes are divided as half and half. Is this making sense? What I'm doing here, how this is working out? I'm just zooming out so you can see all the three. Try to show it sequentially, step by step, what happens if this guy moves and that guy moves, so that you get a sense of what is really going on. Now, let's see if this is also an equilibrium or not. We'll find out if it's an equilibrium or not based on players don't have any incentive to deviate. Let's redraw this. Okay, so what we are saying now is that P1 has moved from his initial position to half, and P2 is still in that same position at 3 by 4. Okay, now let's see who votes for whom. Now the people at 0, then P1 is still the closest candidate and he is still within 0.5 of the policy position. So all of them are going to vote for P1. Similarly, for people at 1 by 4, they're all going to vote for 1. For people at half, now P1 is the closest candidate because he's exactly at half. So now they're all going to vote for P1. They're not going to vote for P2. For people at 3 by 4, P2 is the closest candidate, so they're all going to vote for P2. So on. Also for people at position 1. So now again P1 has increased his vote share. It's now 3 by 5 and this guy is getting 2 by 5. Right? You can think of it in terms of, shifting positions. And see, this may sound very simplistic and very imaginative and very funny sometimes, but this is kind of how policy positions are decided to some extent. Not exactly, because people are not distributed uniformly as we assumed, but that is similar. It's a similar rationale. Let's see. P1 has increased his vote share. P2 will have a similar reasoning. Why can't I increase my vote share? Let me move to half and see if I can increase my vote share. Redraw this and see what happens if P2 decides to change his position. Median voter theorem was, to me, one of the most interesting applications of game theory. I studied this first time, I think maybe 5 years ago or something. And you stop feeling disillusioned and disgruntled with a lot of things, not just politics, but a whole lot of things when you understand the median voter theorem. Really a very simple tool, but it explains a whole lot of things you see every day, not just in national politics, but even at a local level or whatever. Why things don't change? Why does every new, local, not even politician, but local, authority or whoever, why do they still maintain status quo and not do anything? So this kind of explains a whole lot of that. What we are seeing is that P1 was at position half, and now P2 has decided to shift his gears and also move to half. He's like, okay, I'm also going to move to half. Let's see if I'm going to gain something from that. Now let's see who's going to vote for whom. So this is exactly the thinking process. You cannot rush through it. It may take a little bit of time. And as you gain more and more practice, this whole thing will become, this process of detailing things out is going to get more and more simple. But this is the process. You cannot skip it. Okay, you cannot just assume that this strategy is anyways not going to play, so I'm not going to consider it. Game theory doesn't work like that. This is not a simple thing like, oh, x is never going to be negative, so I can ignore negative values from an equation. It's not mathematical in that kind of way. So this is the reasoning methodology. And let's see now what happens for people at zero. For people at zero now, P1 and P2 are, sorry, both the closest candidates. P1 and P2 are both standing at half. Both are equally close to zero. Both are within 0.5 of his policy position or their policy position. So they're going to divide the votes between P1 and P2. So now P1 gets only half the votes from zero, and P2 gets the other half of the votes from zero. At 1 by 4, same story. For people at 1 by 4 also, P1 and P2 are both the closest candidates and they're both within half of the policy position. So again, half will vote for P1, the other half will vote for P2. Same thing for people at position half. See, votes at every position are now equally divided between the two candidates. Okay, people at 3 by 4, same logic. Both are equally close and the votes are equally divided between the two. So you see, in this particular example and in many questions in median voter theorem, there is no prejudice or there's no repetition. Repetition is a technical term used in game theory for attached to any of these candidates. Okay, they are, people are taking them at their word, so to say. Okay, like okay, if you say you're Republican, I assume you're Republican. If you say you're Democrat, I assume you're Democrat. Something like that. They're not going to say, oh, yes, last year or 4 years ago, you were in the Democratic Party. Now you're in the Republican Party. I don't believe you. I don't believe you're a Republican. No, if you say you're Republican, you're Republican. And people are also indifferent to, party colors or party loyalty. That kind of a thing is not there in this question, this setting of the problem. If you are within 0.5 of my policy position, I'm going to vote for you, irrespective of whichever party or whichever, whatever your history might be. So that is an assumption, it's a very big assumption in this problem. And of course, there's a lot of research, there's a lot of, there are a lot of games you can read where this assumption is not upheld. This assumption is, they test what happens if this assumption does not hold. And of course, the games, change a lot with this assumption. So now we can see that P1 and P2 started at the two extremes. Look at the top. This is the topmost diagram we drew, and in this P1 and P2 are at the complete extremes, right? But as they kept shifting towards the center, they kept increasing their vote share. So they kept shifting towards the center until they have now reached, both have reached at the center. So my diagram is not exactly to scale, but I think it is still acceptable enough. And so now when they're at the center, we can check, do they have an incentive to deviate? Now, does P1, we already seen what happens when P1 is sitting at 0 or half or quarter. Now, we want to see what happens if P1 decides to move the other side, okay? Game is not over yet. Let's see what happens. Does he have any incentive to deviate from here? We need to test that also before we declare that this is the Nash equilibrium, because as we said that there are a certain number of people who will not vote if you move too far from their policy position. So what happens if he moves on the other side? So now say suppose this guy was supposed to be a Republican, I gave him a pink color. He decides to actually go and start campaigning in democratic states, blue states, starts taking policy positions which are more for democratic party nature. Say this is, will he succeed? And again, we're not saying that, we are assuming that everybody takes them for their word. They don't care about who you are per se. Okay, now let's see. P1 has now moved 3 by 4 and P2 is still sitting here at half. Okay. Now let's see what's going to happen. For people at 0, now what happens for people at 0? Now P2 is the closest candidate for people at 0, right? P1 has moved. Now you're like, okay, you can move. You'll vote for P2. So all of the people at 0 are going to vote for P2. People at 1 by 4 also. P2 is the closest candidate. They're going to vote for P2. People at half, again, P2 is the closest candidate. So they are going to vote for P2. See, P2 has already gotten 3 by 5 of the vote share. Rest of the game doesn't matter even. P1, he gets what? 3 by 4 for people at 3 by 4, they're going to vote for P1 because he's the closest. And for people at position 1, they're also going to vote for P1. Now P1 is getting only 2 by 5 and P2 is getting 3 by 5. So P1 understands that there is no point in campaigning in the other camp or the other side of the center because now he's reducing his vote share, right? Let me write down the vote share here also. The vote share was half and half, right? At the center, he had a vote share of half and half, but now if he moves from the center, he's reducing it to 2 by 5. And the other guy is winning, he's getting 3 by 5. So he's definitely not going to move to the other side. He will decide to come back. And by a similar logic, if you see for player 2, because it's a symmetric problem, P2 will also not want to move to 1 by 4. He'll be like, I'm losing the game. I'm only getting the votes of 0 and 1 by 4. I'm not getting the votes of half, 3 by 4, and 1. So both the players now do not have any incentive to deviate. Okay. Let me just highlight this. So this, the vote share here, and this is the Nash equilibrium. Something like this. And this is the Nash equilibrium because no incentive to deviate. If you want, if you are not satisfied, you can also consider that rare or weird case in which both the candidates take an extreme position, the same extreme position. And because there is a clause of, stuff, or I'm not going to vote for anybody if they're not aligned with my policy ideological position. So let's see, does that case arise and does it alter the basic character of the problem? So say suppose this is how it is. And now say suppose that 3 by 4. Now both the candidates are, say suppose, standing at 3 by 4. So P1 moved and for some odd reason P2 also decided to move even though he was winning. But we're just testing what happens. We just want to know what happens if P1 and P2 move. Now what about the people who are standing at policy position 0? So now neither candidate is within their policy position. They're all beyond half. They will only vote for somebody who's up till this point half, because there is a clause that they're not going to vote for anybody if they're beyond more than half, away from their policy position. So people at 0 are not going to vote for at all. These votes are lost to both the candidates. People at 1 by 4, P1 and P2 are equally close. So they're going to divide the votes between the two. Like this. at half again, the same method, both the candidates get equal votes. I think here, both the candidates are in the same position. So obviously they're equally close for anybody. And for all of these people, they're within half of their policy position. So again, they're both getting half and half. But now what is happening? They're getting half, not half and half actually. They're getting 4 by 5 ka half. What is 1 by 5 is lost. 4 by 5 divide. Then, yeah, they're getting 2 by 5 and 2 by 5. Sorry, why was this taking so long to? They're both getting 2 by 5 and 2 by 5 instead of half and half. 2 by 5 is less than half. Okay. Oops. Now, because they're getting 2 by 5 and 2 by 5, both will think that, those voters at policy position 0 are completely lost. In this position, they're getting 2 by 5, 2 by 5. Now, from this position, either or both of them will again have incentive to deviate towards the center. Right? I'm not drawing it again because I've already drawn it at the top. But if you see P1 here, if he moves to the center to half, he can regain all those votes from 0. Right? And if P2 remains at 3 by 4 and P1 moves to the center, he will get all the votes from people at 0, half, and quarter. Right? So he wins. He gets 3 by 5 votes. Whereas P2 is remaining at 3 by 4, so he gets only 2 by 5 votes. Now again, P2 will see an opportunity here, and P2 will again want to also move to the center. And again, we are back to the center, which is what we said was the Nash equilibrium. They have incentive to deviate here. So there is some incentive for them to increase this lost vote share at policy position 0. Again, you can also say that, by symmetry, both P1 and P2 are at quarter. Instead of 3 by 4, they both are at a quarter. They lose votes of population at P equals to 1. Right? Again, they have the same incentive to deviate. I hope my handwriting is not so terrible that you can't read it, but the logic I have already explained. Okay, so I have gone over this median order theorem very slowly, taking each step, checking all the cases, because this is sort of slightly non-mathematical problems. So if you have problems in which your strategy is, say, a quadratic function or something, and you need to your payoff is a quadratic function of your strategy or something, all you need to do is just maximize your payoff, get your strategy as a function of the other guy's strategy. That is your best response after maximization. When you want to find the Nash equilibrium, you find at what point both the equations of best responses solve each other. It's a very mathematical, simple approach, right? You don't have to sit and intuit the problem, so to say. But in these kind of problems, like the ice cream cart, the median order, the Braess paradox, even the second prize sealed bid auction, all of these problems, it's not mathematical. How much maths have we used here? Very little. Right? We are not using too much maths here per se. We are, using a different set of reasoning, a different set of tools to approach the problem. And that's why I've gone over it a bit slowly, because I don't know about you, but this reasoning takes a little bit of time to sort of sink in and to develop, so you don't have to rush through it in the beginning, at least. And once you keep going over it over and over again, it becomes more and more easy. Okay, so now I wanted to just go over this two firms example once again. So this is the example. So now we have like 4 or 5 minutes left, and I'm afraid that's not enough time to discuss this, but let me just recap it once. Okay, so there are two firms in a declining industry which cannot support both the firms, and they have the option to exit immediately or the end of the quarter or at the end of the next quarter. And this is the setup. I don't want to read from the slide, the question is given. This is our game table. Let's come to the game table. I just want to explain once again why we used dominated, iterated domination on its strategies here. So in this game, if you see, uh, without going too much into the intuition of it or the setup of the problem, assume like this explanation of how we come to this game table, I have actually given in the previous class. Okay, this whole explanation is there in the previous class. Now let's just look at the game table for now. If firm 2 is playing E, right? What is the best response of firm 1 is N, right? Firm 2 is playing T, then of course firm 1 is better off. Oops, sorry, not sorry. Is better off exiting in the next quarter. And if the firm 2 is also going to exit in the next quarter, then firm 1 had rather exit now. Right? Similarly, if firm 1 is exiting now itself, the firm 2 would rather exit in the, let me use a different color. Exit in the next quarter. If the firm 1 is exiting in this quarter, then also he would rather exit in the next quarter. And if he's exiting now, he would rather exit in the sorry, if he's exiting in the quarter, he would rather exit now. Just saying it the other way around. Okay. So now from here you can see that 0, 4 and 4, 0 are places where you get the best responses of both the players. So these are the two, you can say, mixed, not mixed, pure strategy equilibria. Now, if you want a mixed strategy equilibria, we can actually try to simplify this game. That is the part I was explaining. So there's nothing to be confused. The best response analysis always holds. Irrespective of whether you have dominant strategies or not, the best response analysis is always, it's always going to hold. So it's always true. What we want to do with the mixed strategies and iterated elimination of dominated strategies in a mixed strategy equilibrium is that, sorry, hang on, what the hell? I hope this is clear. Yeah. So what we want to do is we want to simplify the game. If we can find some mixed strategy which is at least weakly dominating pure strategy, then we can eliminate that pure strategy so that when we are trying to find the mixed strategy equilibrium, we have a smaller game to deal with. Now, if it's a 3 by 3 matrix, it's a little bit more cumbersome to solve. We'll have to solve 3 systems of equations. If it's a 2 by 2, it's much simpler, right? Now, if you see the strategy T is dominated by the mixed strategy E plus N. If you take E and N half and half, right? I'm just writing it. Occasionally, it's not very accurate way of writing it, but just to explain what I'm trying to say. So if you play the strategy E by 2 plus N by 2, how does it actually know? Write this, write it here. So E by 2 plus N by 2 utility from this is greater than or equal to utility from T. This is what I'm trying to say. I had explained this last time, but I just wanted to go over it once again. Now let's see. For firm 1, okay, see the first column, or sorry, see the first row. If I am playing E, no, sorry, not first column. If the other guy is playing E, I have the option of E, T, and N. E gives me 0, T gives me 2, N gives me 4. Now, if I take E by 2, N by 2, I get what? 2, which is same as T. It's the same value. Now, if the other guy is playing T, then I have 0 plus 1 is equal to half compared with minus 1, which is greater. If the other guy is playing N, I have the option of 0 and minus 2 divided by 2, which is minus 1, which is again almost same as, not almost same, it's just same as minus 1. So we can eliminate T. And similarly, if you see by symmetry, this guy also gets eliminated. So now in this smaller matrix, you take the probability of say N as P and this as Q, and you solve for the mixed strategy equilibrium, as I discussed in the previous class. So this is the reduced table, game table. And in this game table, now you can solve for the mixed strategy Nash equilibrium. It is not complicated. It's fairly straightforward. Okay. So I hope this is clear. Now, okay, at this part we're done. Let's go to the end. So these are the same books. Actually, there's nothing much difference in the books in this particular. Most of what I've discussed is not from any particular book at all. It is from my own notes. So there's nothing more, unless if you don't have any other questions, then we'll end the class today. And I hope we'll join the class again next week. So if it's okay, I'll end the class here. Okay, all right. Thank you. See you again.